discussing about the flip-flops and all, we'll see that memory decoding. So first of all, we'll see this ROM, kinds of ROM and how the ROM will be. So that is read-only memory. Okay, so we'll discuss about the read-only memory concept right now. Okay, so the read-only memory is like it is for permanent. It is just like a permanent storage here. So permanent binary information is stored. Okay, so unlike RAM, which is volatile, so here read-only memory. So we'll have the non-volatile data. So it will not be erased. The data will not be erased. So whenever the power is gone, so the information that is stored is permanent here. Okay, so the binary information so must be specified by the designer, and it is embedded in the unit to perform the required interconnection pattern. Okay, so we'll follow some patterns here. So the pattern is the way how we design the pattern is called as programming here. Okay, a read-only memory which can perform only one operation, that is a read operation here. It is capable of performing only the read operation, and so 1 minute. We can perform only the read operation, and so it is used to store the permanent data here. So permanent binary information is stored with respect to the ROM here. So the structure of ROM will be like this. So it is just like RAM only, but there is no read and write operation. So only read operation will be there here. Okay. So with the help of k inputs, okay, with the help of k input address, so there will be the size of the ROM will be like 2 power k into n. Okay, 2 power k into n words here. So what I can say, 2 power k into n words, where n will be the number of outputs. Okay, so it will output the number of outputs will be equal to n here. Okay, so this is the structure of ROM here. So k input bits. So already told you about this. So the memory is used to store the address and the instructions and the data, and each memory location will be having the address, and with the help of this address we'll access the instructions or will access the data. So each address will be there here. So if I want to access that specific instruction, the address will be given here, and based on that address we'll access the data or instructions in the memory. So whereas in case of RAM, so we are able to perform the read operation and the write operation, where in case of the ROM we are able to perform only the read operation here. Okay, so we need the address here. So the address size is of k bits here. Okay, so this will be the input part here, the input bits of the address, and with the help of this address we can access up to 2 power k memory locations, and each memory locations will have the bits of size n here. Okay, so here n will be the number of outputs also. Okay, and for example, if I take this consider example of 32 into 8 ROM here. So construct a 32 into 8 ROM. Okay, so what we need here is, so we need 32 locations. So size of the ROM should be of 32 into 8. Okay, so when I say that there is 32, so here we need 32 locations. So memory locations here. Okay, so and size of each location is of 8-bit here. Each location is of 8-bit. Okay, so how can I write this 32 into 8? It is 2 power k into 8 here. So what is 2 power k here? It is 2 power 5. So k is equal to 5. So 5 address bits are needed. So in order to access the 32 bits, okay, so 32 bits. So each memory location is of size of 8 bits here. Okay, so for this, in order to access the 32 memory locations, okay, so with the help of 5 inputs, we'll take the help of 5 into 32 decoder. 5 into 32 decoder. Okay, and these decoder will have 32 inputs, and these inputs are connected to the 8 outputs. So these 8 outputs are connected to the 8 OR gates. These outputs are connected to the 8 OR gates here. Okay, so understand the structure of ROM here. We try to understand the structure of ROM. So wait a minute. Let's try to understand the structure of ROM. The ROM structure will be like this. Okay, so structure will be like this. 32 into 8. This will be the size of the ROM. Okay, so it can be written as 2 power k into n here. So where k here is 5, where k is 5, so n is equal to n is equal to 8. So 8 is the number of outputs here. So we need this number of outputs. Okay, so it is a number of outputs. The structure will be like this. So we need we need 32 outputs of memory. We need 32 memory locations here. So right, so we need 32 memory locations. So what we have to do here is, so I had to use a decoder of size. So the decoder of size k into 2 power k decoder should be used here. So what is the value of k here? So 5 into 32 decoder should be used in order to construct this ROM. Okay, and we need to construct 8 outputs here. So these 8 outputs are taken with help of 8 OR gates. So we'll take 8 OR gates. Okay, so first of all, initially we'll be having 5 inputs here. So I0 to I4, so which will generate 32. So 0 to 31 outputs of decoder here. Okay, and these 32 outputs are connected to 8 OR gates here. So 8 OR gates will be used. So each OR gate is constituting one output here. So this is how we write the OR gates here. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so each is like O0 to O7. Okay, so the ROM construction will be done with the help of all the decoders, with the help of OR gates and the decoders. The size of ROM is like 2 power k into n. So I can construct this ROM with the help of 8. Getting my point here?
Yes, sir.
Yes or no? Yeah. So we need k into 2 power k decoder and n OR gates, to construct a ROM of size 2 power k into n. A ROM of size 2 power k into n. So that is what I understand here. Okay. So 32 outputs of decoder are connected to the 8 OR gates here, each of 8 OR gates. Okay. And so diagram will be like this. So we'll see how the programming will be done later, but diagram will be like this. So I0 to I4, so 0 to 31. So all the outputs are drawn the lines here. Okay, and so there will be a line here. Okay, and that is given to the OR gate. Okay, so that is given to the each OR gate here. So the meaning of this is, so each OR gate can receive the inputs from the 32 decoders. I mean, we have the 32 inputs here, right? So each OR gate is capable of receiving 32 inputs. Is capable of receiving the 32 inputs. So generally we will take the raw OR gate like this. Okay, but here for our convenience, what we can do here is, so we'll take the ROM like this. Okay, so the diagram will be like this here. Okay, the OR gate symbol will be like this. So where we can this is called as array logic here. So or I can write like this, single line. Okay, so generally what we'll do in case of our things here. So normal circuit diagram draw chese method lo, so we can draw like this. Okay, so here this is 2 power k into n ROM size. So we need k into 2 power k decoder, 1 k into 2 power k decoder, and n OR gates. Okay, and all these decoder outputs are connected to each and every OR gate here. So we have 8 OR gates, A0 to A7. So each of the outputs are connected to the 0 to 31 are connected to each and every OR gate here. Okay, each and every OR gate. So I'll take an example of a truth table here. So one truth table. So I'll let you know how the connections will be done here. Okay, so ROM general structure is like this. So the general structure of ROM will be like this here. Okay, so but I'll let you know how the connections will be. So this is we'll take a partial truth table here. So this is not any kind of problem here. So this is a truth table. Okay, so this is a truth table. So from this truth table, so what I had to do here is, so I had to make the connections with the help of this ROM here. So ROM, it is a partial truth table. We'll be having 5 inputs and 8 outputs here. Okay, so and A7 is the 8th OR gate and A0 is the first OR gate. Okay, so it will receive the inputs from, so check the ones here. It will receive the inputs from when the inputs are 0 0 0 0 0, and here for this one and for this one and for this one. Okay, it is like 1 0 1, sorry, 0 2 3, and it is 11101. So 11101 is 168421. 16 8 it is 24, 4 it is 28, and this is 29. Okay, so for 29 and 3 and 2, so this A7 is connected to the decoder output. Okay, so that is what how we have to draw the diagram here. You check here. So that is the diagram here. So with the help of this truth table, so what I have to do here is, wait a minute. Yeah, so this is how it will be. Okay, so what is this one here? So A7 is 0. So I put a cross mark there. 2 and 3 and 29. Okay, so remaining all corrections are not connected here. So only the values which are equal to 1, so those are connected to the respective OR gates here. So A6 is connected to, so 2, 29 and 30. Okay, and A5 OR gate is connected to this one. Okay, so this is how the outputs will be, how the connections will be. There'll be a lot of cross points here, and those cross points will be put a cross mark here. So this cross mark will indicate the connection to this output here. Clear? Okay, so మీ స్ట్రక్చర్ వేస్తారు, ఏదైనా ఒక ప్రాబ్లమ్ ఇస్తారు, ఆ ప్రాబ్లమ్ ఇచ్చిన తర్వాత I have to draw the truth table. That truth table, so with the help of the truth table, you have to draw the decoder here. We have to identify the size of the decoder, and we have to identify the number of OR gates. If 2 power k into n is the size of the ROM here, so we need k into 2 power k decoder, and we need n OR gates here. And after drawing this, so we have to draw the truth table. Based on the truth table, we have to identify the which are the ones. So so the input combinations, so whose output is equal to 1, okay, so are to be identified, and those min terms are to be connected to the output here. Okay, so this is how the connections will be, decoder and the this one. So getting my point, so we'll see one problem, you'll understand it. Okay, so take down one problem and you'll understand the concept here. So take down this problem. So take down this problem. So tabulate the truth table for an the size of the ROM I'm mentioning here. So 8:4. 8:4 ROM to implement the following Boolean expression. Okay, so the problem will be like this. So F1, so take down this problem, F1 of A comma B comma C is equal to sigma of, I'll not write the symbol here, sigma of 367, 3 comma 6 comma 7, and the F2 is equal to sigma of 014. So F3 is equal to sigma of 0256. So F4 is equal to sigma of 2 comma 6. Okay, so this is a problem here. So the size of the ROM, so what I told you, so the size of the ROM, if it is like 2 power k, so okay, so 2 power k into n ROM size. So we need, so what we need here, so we need k into 2 power n decoders, okay, and n OR gates. Okay, this is what needed. So it is 8:4 ROM. So 8:4 is nothing but 2 power 3 into 4 ROM here. So what is the decoder we need here? So we need a decoder of, sorry there. So what is the size of decoder we need?
3 into 2 power 4, sir.
3 into 2 power 4. So how come?
2 power 3, sir.
3 into, so k into 2 power n, right? Sorry, k into 2 power k. Sorry. So k into 2 power k decoder, right? So 3 into 2 power
2 power 3, sir.
3. So that is, we need a 328 decoder here. Okay, how many number of OR gates needed? So we need 4 OR gates. Okay, so we need 4 OR gates to construct this 8:4 ROM here. Okay, so this is the basic point you have to do. So first of all, identify the size of the ROM here, then identify the decoder used. Okay, identify the decoder used, and afterwards identify the decoder used, and afterwards draw the diagram. So first of all, he had given the table of this one. So what is the table here? So we had to implement, tabulate the truth table for 8:4 ROM. So we are told like this. Okay, so we have to tabulate the table for this f of f1, f2, f3, f4. f1, f2, f3, f4 are the outputs here. Okay, and we have inputs of, so maximum of 0 to 7. So 7 working on we need 3 inputs here and 8 possible outputs here. Okay, you can check here. So what I have to write here is, so now we have to construct the truth table. Okay, so truth tables inputs are like, so A comma, I'll take it as A, B and C. Okay, and the outputs column, so we need 4 outputs here because F1, F2, F3, F4. Here outputs here, so it is F1, F2, F3, F4. Okay, so now the truth table will be like this. So 3 input combinations, 0, 0, 0, 0, 0, 1, 101. Right, and the outputs are given here. So already we have this f1 equations, right? So what is the f1 equation? F of abc is equal to, so those are the inputs, so sigma of 3, 6, 7. So for a combination of 3, 6 and 7, so this is 3, 6, 7 అంటే 0 కి 0 ఉండాలి. Okay, and this is also for 0, and for 2 also it's 0, and 3 it's 1, 4 it is 0, 5 it is 0, 6 and 7 both are equal to 1. Okay, so this is for f1 here. So coming to f2. So what is f2? So f2 of abc is equal to 0, 1, 4. So 0, 1, and 2, 3 zeros here. So for 4 it is 1, and remaining it is zeros. Okay, and f3, for f3 it is f3 of abc is equal to 0 to 5, 6. So 0 to 5, 6 it is equal to 1, 0, and this is 2 it's 1, and for 3, 4 it's 0, 0, 5 it's 1, 6 it's 1, and 7 it is 0. Are you following or not?
Yes, sir.
Okay, and f4 it is 2, 6, 0, for 1 it's 0, 2 it's 1, 3, 0, 4, 0, 5, 0, and 6 it's 1, and 7 it is 0. Okay, so this is the truth table here. So the truth table of for the given thing here. So what we had to do here is, so we had to draw the ROM diagram here. So ROM diagram, so what is the size of ROM we told here? So the size of ROM is 8:4. So we need k into 2 power k decoder. So that is 3 to 8 decoder. Okay, so we have to draw the 3 to 8 decoder. So 3 to 8 decoder will have okay, so 3 to 8 decoder will have 3 inputs. Okay, and 8 outputs. 2, 3, 4, 5, 6, 7, 8. Okay, and so we'll get 4 outputs. 4 outputs are nothing but 4 OR gates. So first of all, draw all the lines, 4 lines here. These are the output lines here. So this is ABC, or the inputs, and outputs are from 0 to 7, 0, 1, 2, 3, 4, 5, 6, 7, and so the outputs are given to OR gates. So connections, I'll let you know. So based on the truth table, so we have to draw the connections. Okay, so connections for F1. So check the F1 here. So F1 we will give connections for 0, 1, 2, 3. So this is F1, and sorry, this is F1, this is F2, so F3, and this is F4. So F1 will have connections from 3, 6, and 7. So this is 3, so put a cross mark, and this is 6, and this is 7. Okay, and for next one F2 it is 0, 1, and 3. So this is 0, 1, and this is 3. And don't connect 0, 1, and 3 together. So this is 0, 1, and this is 3. And don't connect 0, 1, and this is 3. And this is 0, 1, and this is 3. And this is 0, 1, and this is 3. And this is 0, 1, and this is 3. And this is 0, 1, and this is 3. And this is 0, 1, and this is 3. And this is 0, 1, and this is 3. And this is 0, 1, and this is 3. And this is 0, 1, and this is 3. And this is 0, 1, and this is 3. And this is 0, 1, and this is 3. And this is 0, 1, and this is 3. And this is 0, 1, and this is 3. And this is 0, 1, and this is 3. And this is 0, 1, and this is 3. And this is 0, 1, and this is 3. And this is 0, 1, and this is 3. And this is 0, 1, and this is 3. And this is 0, 1, and this is 3. And this is 0, 1, and this is 3. And this is 0, 1, and this is 3. And this is 0, 1, and this is 3. And this is 0, 1, and this is 3. And this is 2, this is 5, and this is 6 here. Okay, and the other one, last one is 2 comma 6. This is 6 here, and this is 2 here. Okay, so this is the structure of 8 into 4 ROM here. Clear?
Yes, sir.
Yes, sir.
Yeah. Fine. So this is how the ROM problems will be. So we'll take one more problem. The problem is like, so you try this problem. So we'll see afterwards. I mean, we'll see the types of ROMs. So we'll see the assignment problem later. So design. Wait a minute. Design a 4-bit number square generator using ROM. So there is a problem here. Okay, so we need 4 inputs here, A, B, C, D, and so the outputs, I think maximum of 7 or 8 outputs will get here. So we need to do the squares. I mean, the inputs will be like 4 inputs. Outputs are squares of this. So squares in the sense, so 0 square, 1 square, 2 square, 3 square. So the maximum 4 input will be of 15. So 15 square is 225. Okay, so 225. So the outputs, you have to write the binary equivalent of those numbers. So the outputs are nothing but the binary equivalents here. So 0 to 7. Okay, so we can take it as S0 to S7. Okay, so we'll see that. First of all, we have to draw the truth table. Write the 4 inputs. So write all the 4 inputs. So inputs. So inputs. So inputs will be 4 here. So A, B, C, D. Write all the 4 inputs, 4 possible inputs here. It's like 0, 0, 0, 0. And 0, 1, 0, 1. Write all the 4 possible inputs here. So the outputs will be the squares of this inputs here. So 1, 0, 1, 0, 1, 0, 1, 1. And here it is 1, 0. Sorry, double 1, double 0, double 1, 0, 1. Triple 1, 0. And 4 ones. 1 minute, 1 minute. right? So we have to write the output is like decimal equivalent. First we'll write the decimal equivalent, then we'll write the binary equivalent of that. So 2 square it is 4, so 3 square 9. Okay, so 4 square 16. Write all the decimal equivalents, and afterwards write the binary equivalent of that. Uh, 0, 1, 2, 3, 4, 5, 6, 7. Just alignment ఉండకపోవచ్చు, but we try to adjust that. But you have to understand this. So 169 is 13 square. So 196 is 14 square, and 225 is 15 square. 0, 1 square, 2 square, 3 square, 4 square, 5 square, 6 square, 7, 9 square, 10 square, right? So this is the decimal equivalent. So we have to write the binary equivalents of this. Okay, so write the binary equivalents of this numbers here. Okay, so the output will be the binary equivalent. So the output section, there is the output section here. So we'll start with the 225 first. Okay, so 225 2 powers lo cheyandi. So 2 power what is 2 power 6?
64, sir.
2 power 6 64. 2 power 7
128.
2 power 8
256.
256. So it is less than 256. So 225 is less than 256. So we need powers of 7. So it is 2 power 7, 2 power 6. I mean, what I mean to say here is, so I had to give the binary code here. So binary 64, 32, 16, 8, 4, 2, 1 code. Okay, 64, 8, 4, 2, 1. So 128 is 1 plus 64. So what is 128 plus 64 plus 32? Okay, so 128 plus 60, 180, 190, 190 it's 32, 222. So there is no need of 60. There is no
224.
need of 224 it is, I think. Yeah, and this is equal to 1. So this is the binary code of this. Clear? So 225 binary code is like 111 4 zeros 1 here. Okay, and coming to 196. So 196. So 128 plus 64. So what is 128 plus 64?
192.
192 plus 4. So we'll get 196 here. Okay, so this is how we have to write here. Okay, so this is how we have to write the binary codes of this squares here. Right, so we have to write the binary codes of each squares. So write the binary codes here. So outputs, the maximum possible is 7 here. So 2 power 7. So what I can write here is S7, S6, S5, S4, S3, S2, S1, 7, 6, 5, 4, 3, 2. Yeah. Okay. So for 0, it is all zeros. Okay. So for 1, it is 0. And 4, it's like 0, 0. and 9. One 0 0 1 16 0 0 0. This is 1 and remaining all are zeros. 16 8 4 2 1. So 16 and 25. So what is 25 here? Like S4 S3 or 1 ones. 16 plus 8 24. And we have S0 is 1. Okay, and 36 we have 2 power 5, it is 32. That is S5 is 1, 32 plus 4. Okay, yeah. Write remaining things also. So take down this, and 49 it is like 0 0. So 32 plus 16. So what is 32 plus 16? It's 48 and plus 1. And last one is 1. Okay, and 64, it's 2 power 6. This is 1 and remaining are all zeros. Right, and 81. So what is 81? 64 plus 32 plus 1. Okay, so this is 64 and this is, sorry, 64 64 plus 64 plus 32 will get more values. Yeah, 64 plus 16 plus 1. Okay, and 100, it is 64 plus 32 plus 64 plus 32
4.
plus 4. Right, so fill up remaining things. So next 121. So 121 is 64 plus 32 plus 16 plus 8. Okay, plus 1. So that is 121. 144, it is S7. That is 128 plus 16.
16, sir.
Yeah, 128 plus 16. Okay, and 169, it's 128 plus 1 plus 1. Here, and 196, 128 plus 64, 0 0 0 1 0 0, and 225, it's triple 1. Okay, so this is the truth table. So this is the first important step here. So design a 4-bit square number generator. So we are given the 4 bits here. Okay, those 4 bits is having this outputs here, S0 to S7. And when we are using 4 bits here, so when we are using 4 bits, okay, so what we have to do here is, so how many outputs we are getting here? So we are getting S0 to S7 outputs. So we need okay, so first of all, identify the size of the ROM here. So 4 is the inputs here. Okay, so 4 is the number of inputs. So we'll get it as a K here. Okay, so this will be the K here. Okay, so getting my point here. So inputs and a K, this is the value of K here. So this is the size of the address here. So when we have K here, 1 minute, I'll be back. Right, the value of K is 4 here because the number of inputs here, so we'll be having the value of K as 4 here. Okay, so when we have K is equal to 4, so what is the size of decoder we need here? So we need so K into 2 power K, so 4 into 2 power 4 decoder is the size of the decoder we need here. Okay, so 2 power K is 16 here. So 4 into 16 decoder is needed. So 2 power K into N. So that is the size of the ROM in area. So what is 2 power K here? So 2 power K is equal to 4 here. And ROM size is of, so what are the number of outputs here? S0 to S7. So S0 to S7 and 10 outputs ఉన్నాయి కదా, 2 power 4 into 8 here. Okay.
8.
Yeah, 16 into 8 ROM is needed to design this. Okay, but we can make some modifications here. Okay, so the meaning of modifications is, so we'll identify the we'll check the truth table. So we'll check the truth table whether it is having any zeros or ones or any two outputs are similar here. Okay, so check any two outputs are similar. Okay, so two outputs are inputs are similar here. So any zeros ఉన్న అన్ని zeros ఎక్కడన్నా ఉన్నాయా మనకు? So check this one. We don't have any zeros here. We don't. I mean, we have ones here. So here also we have ones. Here also we have ones in this. Here also we have ones in this. So here S1 we have all zeros. Clear?
Yes, sir.
Okay. And check S0 here. The value of S0. This S0 value is equal to D. The S0 value is equal to D. So these are the two conclusions from the truth table here. Okay, so what we can do here is we can eliminate using this OR gates. Instead of using the OR gates, we can eliminate these two. So we may not use this. We can make this S1 as a 0 here, and S0 is connected to D here. S0 is connected to D. So out of 8 here, so 2 outputs are eliminated. So what we can do here is, so 2 power 4 into 6 ROM can be designed here. So 2 power 4 into 6 ROM can be designed. Okay, so how the designing part will be like this. Okay, so designing will be like this. So 4 inputs A, B, C, D. So A, B, C, D, and we'll get 16 outputs here. So 0, 1, 2. So you write up to 16. Okay, I'm not writing that. So 0, 1, 2, 3 up to 16 values here. Okay, so I told that we need 8 outputs here, but instead of 8 outputs, we'll be using only 6 outputs here, because one of the outputs is like, okay, so 8 outputs, one of the outputs is a 0, one of the outputs is 0 here. So that is, what is our output here? S1. So 0 is given to S1, and so one of the outputs is D. So it is equal to D here. So give that D. So D is given to this S0. Okay, and remaining all we need to use the OR gates here. So use 6 OR gates. Okay, so third OR gate, fourth OR gate, fifth, and sixth. Okay, so this is S2 and S3, S4, S5, S6, and S7. Okay, and the connection should be like this. So the connection should be like S7, the values are 1 1 1 1 for, so these values. So what are these values here? Like it's 12 13 14 15. Okay, so for 12 13 14 15, so if I have 12 13 14 15, so give the connections to that. So 12 13. Okay, so these values, okay, so are given to S7. So give the connections, cross point for the connections here. Okay, for the next one, so S6, the connections are from these values. Okay, so S6, the connections are for these values here, that is 8 9 10 11 and 15 and 16. Now getting the point here.
Yes, sir.
Okay, so this is how we had to finish that. So a cross points pretending. So what are the cross points? So right up to S2 S3 S4 S5 S6 వరకు ఏ క్రాస్ మీ ట్రూత్ టేబుల్ ప్రకారం ఎక్కడైతే వన్స్ వచ్చాయో అక్కడ క్రాస్ పాయింట్ పెట్టండి. Okay, and we eliminated the values of S0 and S1 because S0 S1 will be equal to, S0 is equal to D here. I have given the connection to D here, and S1 is equal to 0. I given the connection to 0. So there we eliminated the usage of 2 additional OR gates here. Okay, so hence, so this is the circuit diagram of the ROM here. Clear?
Yes, sir.
Yeah, so we'll stop it for today. I'll let you know if there is a class in the afternoon session. So if possible, I'll take the afternoon session class by 3:30. Okay, so 3:30 to 5. Okay, so or else tomorrow. Right, drop your attendance and you
Yes,
can
sir.
leave.